So today I wanted to give a brief overview of some of the concepts that you would need in order to do Project 2. There seemed to be some confusion, so I figured a video might actually be the easiest way to kind of get some of the key concepts across. So to do that, what I've done is I've just picked a random topic and the data that I'm using is also random, so I just sort of fabricated the data on the fly just to use as an example for this project. So I chose the topic of Skittles. So this nice little piece of candy here, you can see has a net weight that's given there, and the net weight that it is claiming to have in every bag of Skittles is the mean of 2.17 ounces. So we're just making a whole bunch of assumptions here, but let's just assume that the net weight is 2.17 ounces, and I'm going to argue that over the last year or so, the net weight of Skittles has actually gone down. So I think it's less than 2.17 ounces. So the null hypothesis, or H sub 0, is going to be the status quo. What is the claim, the original claim, going to be? So in this case, the manufacturer claims that the net weight is on average 2.17 ounces. Now, this is somewhat fabricated, so take all of this with a grain of salt. Don't go, fact checking everything, but I just took this off the wrapper. But this is all again just for the sake of example. So my H sub 0, or my null hypothesis, is 2.17 ounces, that the mean is 2.17 ounces. And my argument is that over the last year, that the mean is actually less than that. So mu is actually less than 2.17 ounces. And so if I were to draw this out on a graph, I could put my mean here of the 2.17 that is the claim by the manufacturer, and my argument is that no, it's actually less than that. So I don't know how much less than that, but I know it's maybe somewhere over here somewhere. And so my goal now for this project is to prove that either I'm correct, that the mean weight is actually less than 2.17 ounces by conducting an experiment, or that the null hypothesis is indeed correct in that the average is actually 2.17 ounces. So that's sort of my mission. And so, all the steps I take from here on in are to either prove or disprove that null hypothesis. So what I did was I actually went out and I went out and I asked a bunch of people. I went out to the store. I went out to 10 different stores, and I got 10 different bags of Skittles at each of those stores. And let's just say I weighed each of those Skittles. And so my observations are listed here. So here are my observations. I just threw them into Excel just to, for the sake of time. So the observation number is listed in the first column, and then column B is the weight in ounces of each of the 10 bags that I picked up at all of these 10 different stores. Now, of course, you need to, in your report, you need to rationalize, how your particular sample of 10 is indeed a simple random sample, and that no bias was introduced. And if it was, explain, what that bias might be, and how you might overcome it in a more ideal environment. But for the sake of this example, let's just assume that we've done all of that as part of our report. And so I took these numbers and I calculated the mean, which is this number right here, and I also calculated the standard deviation. Now I just used the functions in Excel to do that, and I ran those functions against this column right here. So I ran it against the weight. And what I got was 2.141 for the mean and 0.03107 for the standard deviation. So now I have some information. I have x bar, which is my mean, in that as I calculated here, is 2.141. And my standard deviation, which because this is for the sample, I use S, this is 0.03107. So now I have those two things calculated. And one of the things that we want to do is we either want to reject or not reject the null hypothesis. So we need to be able to prove that our alternative hypothesis has some validity to it or some statistical significance. So I want to set my significance level right off the bat. And I'm going to set it to the standard 0.05 as my significance level, which is sort of the, out of the box, what a lot of people choose for their significance level. And so I pretty much defined everything I need in order to move forward. So now I need to actually figure out, well, what is my p-value here? So to compute my p-value, I first need to compute my t-statistic. And so to do that, I use t is equal to this formula here, x bar minus mu sub 0, which is our null hypothesis mean, which in our case would be 2.17 ounces, over S divided by, that's an S, divided by the square root of n. So we're adjusting our standard deviation for our sample size, which we do whenever we're dealing with a sample. So if I plug all the numbers in here, we should get 2.141, which is the x bar that we got using Excel, minus 2.17, which is the null hypothesis mean value, divided by that standard deviation that we got, 0.03107, divided by our sample, the square root of our sample size, which is the square root of 10. And if I do all the math on this, you should get negative 2.95 as your t-statistic value. Now, if you remember, for the t-statistic, we need to use table C. So if we look in table C, we'll also notice that we need to know what the degrees of freedom are. Now we know that our sample size, and I forgot to write this up here, our sample size was 10. We took 10 observations or 10 weights of 10 different bags of Skittles. And so, sorry about the dog, and so our degrees of freedom will therefore be 9, or 10 minus 1. So if I look in table C, and I can't really bring table C up, there's not enough real estate here, but if I look in table C, what I will find is that on the row with 9 degrees of freedom, I will look for 2.95. Now, the negative and the positive don't matter, because the negative just means I'm looking to the left or I'm looking for a value smaller than the null hypothesis. If it's a positive value, it's just saying I'm looking for something that's greater than the null hypothesis. So the signs don't really matter in this case, so we can just get rid of the sign and just look for 2.95 on that row of 9 degrees of freedom. And what you'll find is you'll find two numbers that this 2.95 falls between. In the I call them the bracketed numbers. And these are 2.821 and 3.250. Now, if you follow these down, these two numbers, these two brackets, down to the row, so follow to the row where it is a one-tailed number, a one-tailed test, then you'll see on that row that the 2.821 and 3.250 fall between 0.01 and 0.005. And this is our p-value. This p-value can now be compared to the level of significance. So if you recall, our level of significance was 0.05, and our p-value is clearly less than. So no matter what I pick in between these two numbers, it's still going to be less than 0.05. So our level of significance is greater than, or our p-value is less than 0.05. Therefore, we reject the null hypothesis, which means that I have now provided some level of statistical significance to argue that the bags of Skittles are indeed less than 2.17 ounces on average. Now, in the next part of this, I'll go through the confidence interval side of this, but I've run out of room, so I think I can keep going here. So let me erase this, and we'll go back to, and I'm just going to get rid of our Skittles here, because we don't really need that. And actually, we don't even need our data set at this point, so I'm just going to clear that out of the way as well. And what we're going to do now is we're going to work on our confidence intervals. So the assignment for Project 2 wanted you to find the confidence intervals at 3 different levels of confidence. One was at 90%, 95%, and 98%. So I'll do one of each. So the first thing we want to do is we want to identify the formula that we're going to need to do each of these different confidence intervals. And it's the same formula no matter which confidence interval we're using, or which level of confidence we're using. So let's just put that right out there. So that's going to be that X bar plus or minus, remember plus or minus means give or take, the t statistic, or I'm sorry, the critical t value times our sample standard deviation divided by the square root of n. And so this is the formula that we're going to use for all 3 levels of confidence here. Now, the one thing that's going to change in all 3 of these is really just going to be this guy. So at each level of confidence, this T star is going to be a little bit different depending on the level of confidence that we're targeting. So let's just go through. So at 90%, we'll do that one first. So we already know, and we established this before, that X bar, I'll just put them over to the side, equals 2.141. S is equal to 0.03107. And N equals 10. So we know all of those. And we also, those are the only things we really need to know at this point. So we know those 3 things, and at 90%, we can figure out what that T star is. So if we go to the table in the book, Table C, we can look at Table C, and you'll see that for the degrees of freedom, and again, we've established the degrees of freedom are 9. In this row, at the column for 90%, we get a T star of, and I'm just looking at my notes here, T star of 1.833. That is our T star, and that's simply just by going into the notes, or into the table C, going to this row 9, column, the column that lines up with 90%, and finding the value that those two intersect at. And so this is T star. And so now we can pretty much plug everything else in. So we have X bar, 2.141, plus or minus T star, which is 1.833, we just looked that up, times S, which is 0.03107, over the square root of N, which is 10. Now if we do the math on this, we should get 2.141 plus or minus 1.833 times all of this simplified, which is 0.0098, and I'm rounding, which in turn gives us 2.141 plus or minus 0.018. Now, if I were to graph this, here is my mean right here. Now this is my sample mean, so this is 2.141. This is X bar, which I'm approximating using to approximate mu. But the big difference here, as opposed to what I was talking about in the last part of the problem with the p-values, is that now I'm approximating the mean, give or take, with some level of confidence, some value. So give or take, meaning it's between, or an interval between two values. And in this case, it would be, if we do the math here, I think this is, this is a 1, 2, 3, and 2.159. So this is 90% confidence level here, or this is the interval associated with a 90% confidence level. So all that was 2.141 minus 0.018, and this was 2.141 minus 0.018. And essentially the last three are doing the exact same thing, except my t-value is going to change for the different levels of confidence that I'm looking for. So for 90%, we got 1.833 from the table, but for 95%, and I'm just looking it up right now, but for 95%, we should get 2.262, and for 98%, you should get 2.821. So these are the three values that will change, and they're the only three values that will change when we do these computations of the confidence intervals. And what you'll find is that this interval will keep getting broader and broader the more confidence you add to it. So it'll just keep going outward here. And it won't be by much in this particular example just because of the precision, but you may find that you have a much broader range of numbers than I have here. But for all intents and purposes, it will go outward as you increase the level of confidence. So hopefully this is helpful. Again, the book is asking you to not only to do, or not the book, but the project description is asking you not only to do this by hand, but also to go through and do the equivalent for a few of these in Excel. So use the Excel templates that we've gone through to work through those parts of the problem.